Speaker is Ben Glocker from Imperial College, works at the interface of imaging and AI, and he's going to be talking about computational tools for improved image-based detection and diagnosis of disease. So, Ben.
Thank you very much. I'm really delighted to join this event and for the opportunity to talk a little bit about our work, but also I want to try to bring some food for thoughts towards the end of the talk. So we'll see, hopefully there's enough to discuss in the breakout sessions. So I wanted to give you a bit of an overview of some of the technology that we are developing in the context of detecting disease. The focus on cancer, but there's also some non-cancer things I will be mentioning. Just a few disclosures. I do work with a few companies. Some of the work I'm talking about is related in some sense to the work I'm doing with them. But mostly, this is about the work coming out from the Biomedia group at Imperial College London. It's a big group in the Department of Computing. So most of these people are computer scientists. A lot have a background in statistics, math, physics. But we are really focusing more on the development of methodology, new algorithms for analyzing medical scans. And these days, a lot of the work is at this intersection of using machine learning or AI technology for doing medical image analysis tasks. The research in general that we are doing in our group is, as I said, focusing very much on the development of algorithms and new methods. But of course, we have applications and we work very closely with clinical collaborators on clinical applications like detection of disease. We more and more realize that if we want to actually bring this technology into clinical practice, there is still a lot of work to be done on making these algorithms more robust and reliable. So we have quite a few people who are actually focusing on machine learning methods and theory and how we can improve on the theory to then also get more reliable tools that hopefully eventually we can use in clinical practice. And I know the second talk by Jorge Cardoso will talk a lot about how we get there, how do we deploy, for instance, these algorithms in the NHS. So I want to just give you a brief overview of the different types of applications that you might have come across already. They have been discussed a lot. Also now in mainstream media, there's a lot of discussion about how AI can help to detect cancer, for instance. We have been working a lot on brain in general, so brain lesions, detecting, segmenting, so basically quantifying lesions in brain. So this is an example of traumatic brain injury, but the algorithm that we're using here, as I will show you, can also be used, for instance, for brain tumors. A very early application where people used deep learning or advanced machine learning techniques for skin lesion classification. And there's a lot of interest, for instance, also to deploy such techniques in screening. So in cancer screening, for instance, like breast cancer screening, where the goal is to detect suspicious signs of a potential cancer in mammography scans. So one of these algorithms, just to give you a bit, maybe for some people who are not too familiar with the type of technology that we are developing and the type of methods, just to give you a quick idea about one type of algorithm that we developed in our group called DeepMedic. So this was specifically developed for brain lesion segmentation. We started with brain tumor, but then saw that it actually works in other types of pathologies as well. So this is a convolutional neural network. So this is, of course, just a schematic. But basically what it does is you take a input image, or you take an image as an input here. So this would be a 3-dimensional brain MRI scan. And then this convolutional network learns to extract features from that image. And it does it in a way of building up a very complex feature representation towards the end of the network. And this is done by successively applying so-called convolutional layers. So basically what this means is what you're doing is you learn features of features of features. And that is different from standard machine learning, where you only put in maybe even semantically meaningful features, which are then used for making predictions. Here, the feature representation itself is being learned as part of the training process of the algorithm. Here, just some visual examples of this, that this really works quite well. So this is a glioblastoma example, so brain cancer, where the goal is to segment out the different parts of the cancer. So we see in red is the necrotic part of the tumor. The yellow bits are the active part, where this is the proliferating part of the tumor that infiltrates the brain and is very active and has high metabolism. And then around that tumor, you typically have edema, the swelling, water-enriched areas. And it is important to be automatically able to quantify the tumor, for instance, if you want to monitor progression, or if you want to monitor how well a certain treatment might work. If you want to see if a drug, for instance, can turn active cells into necrotic cells, you need to be able to very accurately extract that information. What we are showing here, so I'm flicking forth and back here for a few examples, is what a human annotator would do and what the machine would do. And I probably don't even need to tell you which one is which, because they don't vary too much. There is, of course, a bit of difference. But again, if you actually ask 5 different human experts to annotate these scans, you also get a lot of variation. So in these kind of examples, you see that this machine learning technology is actually quite mature and can do some of those tasks quite well. So here's another 3D visualization of a similar example, a glioblastoma tumor that has been automatically detected. So you see this kind of heat map, but the detection is not that difficult. But now the accurate separation of the different parts of the tumor in 3D really allow you to do accurate quantitative measurements. And of course, you could now think about applications where you do this over time. For instance, if you want to do lesion progression, monitoring of lesion progression. And that's what we did in traumatic brain injuries. So the same algorithm, the same underlying technology that we use for brain tumors, we could also use for traumatic brain injuries, which to us as computer science do look quite similar in the sense that, yes, they also appear to be like abnormal things in the brain. And if we train the similar algorithm, but with different data, we actually also get quite good results. So there's a tool, BLAST-CT, which is publicly available. So this has been released as open source, and this can be used for other diseases. Now, if you have your own data, you can retrain these algorithms. So in this paper, we just showed that you can do exactly these things of estimating the lesion volume. You can monitor over time if you have scans over time. And that really informs then, first of all, clinical research, but maybe eventually also clinical decision-making once these tools are properly validated. And I will come to that. So what about other types of lesions? What about nodules, for instance, that you might find in CT? So this is a quite daunting task for radiologists when they need to look for like the needle in the haystack. When you have like whole body scans and you need to look for suspicious regions, that's really difficult. And again, that is something where maybe algorithms can help us. And what we found so far is that machine learning can help us if we have lots of examples. So here, for instance, is an example where we used a publicly available data set that has a lot of CT scans with expert annotation. So this is a data set released by the NIH a couple of years ago. It has 32,000 CT images. And in each of those scans, humans have annotated lesions. All kinds of lesions. So this, again, not just cancer, but there are, of course, also cancer lesions among that. And again, then you can design algorithms. So this is a slightly different algorithm than the DeepMedic one. So this was one that we developed a few years back. Now, these details don't matter too much, but what is interesting about this algorithm, that it takes basically as an input bounding boxes. So that is how the annotations have been done in the scan. So someone draw a bounding box around the lesion. And that information is being fed into the algorithm, but then the algorithm itself also, from the bounding box information, tries to do a segmentation without having that in the ground truth, without having a reference segmentation. So we can derive some rules, and based on the appearance, we can come to what is close to being actually a nodule segmentation. Again, that would allow us to, for instance, measure the volume of the nodule. This worked really well. So this algorithm that we developed, we compared it to various different previous works. What was surprising to find is that the algorithm that we developed that tries to also do the segmentation at the same time had a very positive effect on the detection of small lesions. And that is quite important because the big ones, they are typically relatively easy to spot for even within a few seconds or minutes. If a radiologist goes through the stack of images, they will find the big lesions. The small ones are the ones that are important to detect early because they are often, we know that we can still treat or do interventions. And also we want to see, for instance, how these lesions progress. So detecting small lesions is important. That is what we could do with this algorithm. However, if you look at these plots, and we can discuss about this in the breakout session, while we got reasonably good results, so we were able to publish this, for clinical use, this is still having a way too high false positive rate. And I think that is the other side of these algorithms. They do a good job in detecting things. But for instance, this one was way too sensitive. So it detected many other things that weren't maybe suspicious or weren't of concern or weren't even lesions. And then, of course, you have to think about what do you do in practice when a human has to now look at all the things that are flagged up. Just to give you some visual examples, again, it does reasonably work well on the average case or on average. So here we see in green when the algorithm detected correctly a lesion that was annotated with a bounding box shown by in yellow by the human. Sometimes it detected things that didn't seem to be lesions. Interestingly, sometimes it detected things that clearly seemed to be abnormal things, but that weren't annotated in the data set. And that is a thing that we find all the time, because obviously these manually annotated data sets also, first of all, contain errors, but they also not always contain all the annotations that are needed. Sometimes they have only annotated the most obvious lesions and some others were missed. So here's an example, for instance, where the algorithm nicely found this lesion in the left kidney, and then it also found something in the right kidney which wasn't annotated at all. But I, at least from my non-expert eye, I would say there is also something suspicious here. So one might even now use these algorithms to actually go through large amounts of data and automatically annotate them, and then have a human afterwards to go through and maybe remove the false positives and clean up the annotations. And that is a quite effective way of getting to very large amounts of annotated data to have this kind of semi-automation. So we have put this spot the lesion tool into a little game a few years back. Computer science students from Imperial have made a game that you can play on your smartphone or your computer. So if you go to spotthelesion.com, you can actually try to beat the AI in detecting lesions. And it's interesting. You will see how quickly you will get better and better in these things. I want to mention just another application. This is a current project that's ongoing. So this is led by Professor Andrea Rocal at Imperial College, where we are looking at multiple myeloma, and that's a collaboration with the Royal Marsden and the Institute of Cancer Research funded by the NIH. And here we are looking at detection and classification of myeloma. So this is using whole body MRI, which is a relatively new imaging modalities in the setting of cancer, I guess, in general, but in particular in myeloma. Now, bone cancer spreads across the whole body. So a modality that can assess the entire body or can capture the entire anatomy of the patient is important. There's a lot of clinical work that has shown that whole body MRI has a role to play. It is now also the recommended imaging modality in the NICE guidelines for multiple myeloma. However, the problem with whole body is that, again, similar to the lesion problem I mentioned earlier, is that it's a lot of data to look at. So if a radiologist needs to look through these whole body scans, it's very time consuming, and it's also not easy because they don't just look at one single image, but actually these whole body MRIs are typically multispectral, multi-channel images where you have an anatomical scan, for instance, a fat and a water scan. You have diffusion scans that show up certain types of lesions, but also other things. So you need to basically do this, what was mentioned earlier, this multi-model fusion to really read those scans, and that is tricky. So again, algorithms might help us. So here we developed an algorithm which is interesting in a way that it tries to locate where the lesions, where the cancer is and what type of cancer. So we are doing a classification between non-active, focal, and diffuse disease. with a network called multiple instance learning. So what this algorithm is doing, it only knows for the entire patient, so a patient level label, whether there is disease or not. But then it takes out patches, so-called instances, puts them into a bag and tries to classify that bag, whether that bag has at least one positive example, positive in the sense of the disease label. And then it tries to work out by having weights on these instances where the lesion is. So here in this example, for instance, we could identify where the lesion is, where types of the bone cancer do show, without actually knowing, without having any annotations. The only annotation, the label that we have is on a patient level of saying, okay, this patient has a focal lesion. And now the algorithm tries to figure out where that is. So that is quite promising. It's still preliminary work, but I think it shows where this technology can go, which I think is really promising. I want to finish off. So these were just some examples of, I guess, mostly work that we have been doing. Of course, there's a lot of other work in the area of AI for cancer screening, cancer detection, cancer classification. Also in other imaging like histopathology, which is a big area I haven't talked about. But I want to finish off with some thoughts that are maybe interesting to pick up in the breakout sessions. And that relates to my point of validation. So if we are developing these tools and we publish papers and we show that they are effective in our data sets and so on, when can we do the next step and when can we bring them into clinics? And I'm sure George will talk more about this, but one important point is, how do we actually assess that they are safe, that they are ethical to use, that they are doing the right thing? And I'm just listing a few things here, and also different perspectives, because different stakeholders come in at that point. Of course, we have societal perspectives. Patients want to know how these algorithms work. There needs to be transparency. We want to make sure that these algorithms act in a fair way, that they don't amplify disparities, or that they treat different subgroups, patient subgroups differently. Of course, I focus a lot on the algorithm perspective, but of course, there's a lot to be done on from a clinical perspective. How can we do proper studies to check how well these algorithms work? And there are quite a few initiatives now across the country, across the world, looking into how can we properly evaluate AI. I just want to raise this point here. So if you look at the NHSX so-called bias guide for AI, they do mention specifically some points which I think are worth discussing, which, of course, retrospective validation is one point. So you run your algorithms through a curated data set, maybe even with an external third party, to check that the performance is as claimed, right? The other thing they mention, and I think this is really important, but also interesting to discuss, is what about model safety credentials? So they say if you are in the position of procuring or buying such a technology, you should assess things like robustness, fairness, explainability, and privacy. I'm not talking about privacy here now, but it's also an important aspect. But how do you do this? So if I give you one of our algorithms, how do you check whether this algorithm is robust, fair, and whether it can explain its predictions? I personally believe there's still a lot of methodology and tools and frameworks missing for doing this. And for instance, the bias guide is interesting because it mixes robustness and reliability, which I think are two different things. For instance, robustness for me concerns an algorithm's ability to preserve its performance under variations in the input data. Think about moving between different hospitals. The scanner might change, your patient population might change. You want that your algorithm performs robustly under these variations. Reliability, on the other hand, concerns for me the question whether I can trust the output prediction. Now, the two are related, but reliability is kind of different, because when the algorithm makes a prediction, it would be great if the algorithm can also say how confident it is, and this confidence needs to be trustworthy. For example, an algorithm should tell us when it's completely unsure and when we should discard its prediction. So there's still a lot of work to be done on the methodology side of things. I will probably skip this, but just to mention, there are some ideas how we, for instance, measure robustness through so-called perturbations. What you do is you change your images in a controlled way, and you see what happens to the predictions. There are sometimes concerning things. So some of you might have come across so-called adversarial perturbations. Now, these are perturbations that are specifically designed to fool or to trick one of those algorithms. For instance, we know that you can add certain types of noise patterns to images, which are imperceptible for a human, which change the prediction. You can either make, for instance, in the skin lesion example, add a certain noise pattern. Suddenly all these skin lesions are predicted to be of one type, right? Even if they're actually very different. There are also noise patterns where you can specifically change, for instance, a chest X-ray that looks normal, and you can change the algorithm to say it's abnormal and vice versa. So now this might be concerning that this is possible. I'm less concerned that this would happen in clinical practice because you need to have access to the inner workings of the algorithm. But it's interesting that it is possible, which tells us a little bit how these algorithms, tells us a little bit about how these algorithms behave and work. So it's important to study this. Reliability, on the other hand, so we want our confidence estimates that an algorithm produces to be well aligned with its actual accuracy, right? So when the algorithm says, I'm 70% certain, it would mean that in 70% of the cases, the prediction is correct in that category, right? Another work that we've been doing on brain tumor segmentation, again, is to bring in uncertainty in a way that we can produce multiple outputs. Here's an example from lung nodules. If you ask 4 different experts to annotate lung nodules, you get 4 different answers. Can we incorporate that type of uncertainty into algorithms? Can, for instance, our algorithm not just produce a single output, but actually produce multiple outputs? And how could we use that? We can, for instance, either like have an expert and overwhelm them by actually showing not just one prediction, but multiple, or we can use it, I'm skipping the details about the results here, or we use it to measure the uncertainty. So if we can produce multiple plausible predictions, we also get a notion of where we would vary, where these predictions are varying. So we get an idea of where are we more or less certain, for instance, about the segmentation. And that might, for instance, feed back into, let's say, radiotherapy planning, where you draw contours, where you say these parts need to be irradiated. If you can put in uncertainty estimates as well, you might do better planning of radiotherapy. So just to conclude here, so I think there's a lot, and maybe that's for the discussion round, to talk about not just the algorithms that we develop, but also what can we put around there? What type of safeguards can we put before and after an algorithm? What do we need to do to make these algorithms more transparent and explainable, so that at the end, everyone who is affected by the use of these type of techniques has a certain level of trust. I'm stopping here. Thank you very much.
So thank you very much for that talk. That was really excellent. We've got about 4 questions in the chat, and we've got just 2 or 3 minutes to get through them. So maybe I'll just read through the first couple. So first of all, what the number of data sets that you use when you're doing algorithm development? So I guess that means, how many scans and so forth. It varies a lot. So the universal lesion detection, as we call it, uses like a couple of tens of thousands of scans, and that is really needed to get to an accuracy that is acceptable. We know that, for instance, for screening applications, people build algorithms, for instance, for breast cancer screening using millions of images. But you don't always have that, right? So for brain tumor segmentation, for example, it's interesting. We can work with a few, maybe even less than 100 scans to already get an algorithm that has seen, let's say, 80 scans of humanly annotated images to get to a level that you could say it's getting close to like the human variation. So it really depends. There's not a one answer. So very problem specific. And then another one, are there particular types of algorithms that are suitable for specific types of medical imaging, or is it more generic than that? So it's interesting. So I guess it depends on what level of like detail you want to discuss. I guess you could say generally deep learning is a very general tool. And deep learning, I mean, I'm happy to discuss about this later, but what are the specifics of deep learning? It comes down to how you design the algorithm, the architectures of these neural networks that we are using. Then yes, you would find specific architectures are useful for specific tasks. But as a general, going higher level, deep learning is currently the way to go as a tool. And we find, especially for image-based prediction models, they are just the best that we can find in terms of predictive accuracy. Okay, 2 more questions. I think we're done. First of all, I guess this is a robustness question. How does the performance vary across different scanners? Again, it depends on the application. We find in MRI,
it varies a lot. So MRI is a tricky modality. You do find, whether you use a Siemens, a GE, or whatever scanner, that there are variations in the data that the algorithms are susceptible for. So if you train, let's say, only on one type of scanner, we often see performance drops of 5 to 10% if you go to another scanner. So there's a lot of work needed on like the data harmonization.
Okay, fine. And then one more, and then that'll be it. This is just the one. In your experience, what is the expected acceptability of the techniques by practitioners?
You would have to ask the practitioners, I think. They will give you different answers. I think, to be honest, at the end of the day, doctors need a certain level of trust in these algorithms. And that's what we need to work on. And I'm sure maybe George will talk about this a little bit, how we get there. I think generally it is important to have everyone being involved in the development process, right? So if also patients, right? If we just go out and say, look, here's my nice algorithm, use it. No, I mean, they need to be on board from the beginning, even at the design stage and at the data collection stage, and all like throughout the whole development cycle. And I think that's how we can gain trust.
Great. Okay, so thank you very much for that. That was really excellent. And on that note, let's move on to Jorge Cardoso, who works at King's College, also in AI. Set up some startups, and he's going to be talking about stuff like how to work with the NHS, big data, and so forth. So, George.
Excellent. Can you hear me well, and can you see my screen?
Hey.
Yeah. Yes.
Just making sure.
Thank you, George.
Okay, so good morning, everyone. I'm going to give you a bit of a glimpse of what we are doing at King's College London and the London AI Centre to try to go on the journey on how do we do research and how do we develop AI models and how do we deliver AI models in a healthcare setting for the purpose of cancer diagnosis at the scale of the NHS. So the problem that we have and that we're trying to tackle is really the problem of the biomedical revolution, massively improving the quality of care that we've been providing to our patients for many years. But the cost of that revolution, of that care provision, is increasing very substantially, much beyond what the current inflation looks like. So the cost of care is increasing, and is increasing because the technology is becoming more complex. The kinds of things we can do to patients is becoming more complex, more personalized, and more expensive at the same time. And the one way that we have to continue improving the quality of care without making healthcare too expensive is through the use of automation and technologies that make healthcare cheaper, either by making sure that some people don't develop certain diseases by diagnosing them earlier, for example, or having better treatments, or to make sure that if people are being treated and cared for, that the care provision is more efficient and at the same time slightly cheaper, so that we can achieve the same outcomes or possibly even better outcomes for the same costs that we have at the moment. So when we think about AI in healthcare, as scientists, we normally think about improving patient care as the premise. We think about how do we diagnose patients, we think about how do we prognose patients, we think about what drugs should we be giving to these patients, what are the optimal treatments, the optimal interventions. But this is just one small drop in the full healthcare process and all the things that AI can have an impact on in the healthcare setting. It's just that we as scientists, we tend to think about this as the primary end goal. Another way that AI is currently already impacting healthcare is through clinical efficiency optimization. What I mean here is any process that has to do with data preparation, measurement extraction, being able to summarize information, being able to display information to clinicians, being able to make sure that things are prepared in time and available at the time of care. So anything that makes the service care provision itself more efficient so that they can care for more patients and have the best information available to them at the time of care. Obviously, this is related with improving care, but it's actually a procedural improvement through the use of AI. And AI algorithms are being used to make sure that the data is collected properly and that is well curated. Another part that AI is starting to take a big footprint in the healthcare setting is auditing. So we tend to audit our clinical services every 6 months, every couple of years, to make sure that we're caring for patients with the right level of accuracy and service, right? But what happens is sometimes 2 years down the line, you realize that maybe your service care provision hasn't been up to speed. Maybe there was some part of your treatment pathway which was not optimal and was actually causing a lot of problems. But you tend to find this out maybe 6 months, maybe a year down the line. We would much prefer to have systems that are continuously checking what is happening in our hospitals and making sure that the statistics and the quality of care and the outcomes are hitting certain performance targets throughout the year continuously. And so that we can see that any degradation in those performances can be translated into something that can be actioned and improved. Right? So we want to find something that is wrong with our hospitals and the way we care for patients before you actually harm anyone. Another part that I think is incredibly important is how do we even manage an hospital as a whole? If you think about how many beds a specific clinical service is going to have available tomorrow, or who's going to miss their appointments, or where is this patient going to be in a week's time, in what clinical service is this patient likely going to be in. If we can predict all of these things, we can not only start having more people going through our hospitals, for example, by making sure that we book appointments that take into consideration that some people are likely to miss their appointments, but also that we make sure that we have enough beds available, enough clinicians, enough nurses available, because we can predict a few days in advance where the patients are likely to end up going and needing to go to be able to receive the care that they need. And some of these systems can be predicted at the overall scale. For example, some hospitals do have a relatively reasonable picture of what happens, for example, throughout the year, but they wouldn't know on a per month basis. They wouldn't know the difference between a Monday and a Saturday. They would have very hard difficulty to cope with natural variations that happen all the time due to things like pandemics, right? So having systems that can dynamically know how do you improve the operational efficiency of hospitals would be ideal. And if you put all of these things together, and if you try to optimize the patient journey from admission to discharge and all the steps that you go through, this is really the aim of value-based healthcare, is how do we make sure that we can have the best outcomes for the least amount of cost possible and optimize everything in one go rather than making sure that each one of the steps themselves are optimal. How do we make sure that the journey is optimal? So in order to tackle all of these different questions, we have created this, or we were awarded this London Medical Imaging and AI Centre for Value-Based Healthcare, which actually now is on its second tranche of funding. The first of all was from UKRI, the second one was from the Office of Life Science. And this partnership has grown from a relatively small partnership between 2 universities and 3 hospitals into now where we have 4 of the London biggest universities, so UCL, Imperial, Queen Mary, and King's, and also 10 hospitals in London and southeast of England, which cover roughly 1/4 of the UK population as a catchment area. And this AI Centre now is trying to create platforms and ways to collect data, do research, develop models, and deliver models across all of these trusts in a standardized fashion. In order to be able to do this, we need to go through a series of steps. In this specific presentation, I have it in 9. I've broken it down into 9 steps. So I'm going to take into 9 steps that you need to go through to make sure that AI can even be a reality in a healthcare setting. So the first part that you need to tackle is how do you even, and this obviously applies to cancer, but it also applies to pretty much any other pathology out there. Cancer is even more multimodal than most pathologies because it tends to have multiple omics playing the game, but the concept is still the same. So for you to be able to deliver AI in a healthcare setting, you need to make sure that your healthcare records, your patient electronic healthcare records, your EHR, is standardized and harmonized into the same data types and the same ontologies. So you need to make sure that your clinical data is mapped from your clinical systems, your EHRs, into a standard that is accepted, that is open standards-based, and that can be recognized by an AI algorithm. Because if an AI algorithm is going to use, for example, blood measurements to make a prediction of something, the blood measurements need to arrive at the algorithm, and the algorithm needs to know which blood measurement corresponds to which type of measurement, and what are the units, and what was the excipient that you use, and all of these other details. So everything needs to be incredibly well standardized so that the algorithms can make sense of them. What you've seen so far in the AI world is that people tend to focus on relatively well harmonized settings like medical imaging, because images themselves tend to be are very much standardized. There is a very strong standard of how we communicate with them. But when you go to other omics, other sources of data, that's where the harmonization becomes absolutely necessary. Step number 2 is the fact that at least in the NHS, and many other countries the same thing, maybe not so much in the US because they have scribes that translate information, but in most healthcare systems in the world, a lot of the information that exists in the healthcare systems is not in the form of nice structured data in tables. It's actually natural language text and clinicians that write letters to each other and pieces of text and reports. So they would describe a patient and their condition and the symptoms and all of these things in the form of text, sometimes by dictating to a device, sometimes by actually typing it themselves. But obviously this text is very complex, even though it's also very rich in information. It has a lot of spellings and typos. Clinicians tend to use acronyms and certain types of nomenclatures that sometimes are a bit ambiguous. For example, if you were to say, if you were to write HR, it could mean heart rate, but it can mean per hour. And those terms obviously mean different things depending on the context around it. So it's not just knowing the word, is understanding and how do you disambiguate between how the word is used in different settings. Clinicians also like to negate things. So they like to say what the patient doesn't have because they've checked for it. And they also like to talk about family history. So for example, if you say someone has a family history of cancer, it doesn't mean that someone has cancer. It means that they have a family history of cancer. And these things need to be understood by the algorithm so that they can make the right assertions about the data. If you can identify all of these different concepts, what you can do is you can start building this ontological graph and this knowledge graph that relates these concepts. So if you use these standard ontologies and standard data models, and you can identify that, for example, someone is taking ribavirin, which has a specific CUID. So this is the identifier of this drug. The ontological graph tells you that this is an anti-hepatitis C agent, which treats hepatitis C, which affects, for example, the liver. So you can use the fact that someone is taking this drug to know that the patient has some form of condition that affects the liver, and thus the patient, for example, is not a healthy patient from a liver point of view. So you can start making these complex relationships by using the ontological graph behind it and by being able to identify all of these terms. And that means if you want to search for all liver patients in your hospital, you can use, for example, pharmacy data to be able to infer who those patients are. So you can extract and pull out the data that you need to train your algorithms at the scale that is necessary to make them accurate. The third step is we need to use this ability to identify all of these concepts to be able to identify care processes. These plots that I'm showing here, the one on the top right is a very large international US-led study that had more than 100 people involved, where they were trying to figure out the use of specific stroke drugs in different countries throughout the years. And this was collected by hand. While the image in the middle, in the top, was done at King's College Hospital, one of our partner hospitals, in a couple of afternoons by a single person. And you see that the patterns are very similar. Obviously, they have different noise characteristics because the one on the right is many, many sites and the one in the center is just one single hospital. But you can get very similar patterns in a very quick amount of time because you have the mechanisms to be able to search and query this data. But because you're doing things automatically, you're doing things algorithmically rather than by hand, you can then start asking more complicated questions. For example, you can say, well, I see that my patient is taking a specific drug like warfarin with a specific dosage, and now this dosage has been escalated to this other dosage or this other drug. Can we try to figure out why that has happened? And then you can create, for example, plots like the one you see below, where you see transitions between drugs and their dosages or their different subtypes until the patient, for example, has converged into a specific drug where they are stable. So if you now take all of these information into account, right, you start really understanding how patients are treated for. So you take the medical history, you do a cohort selection by doing search at scale. For example, you might search for anyone that has a primary diagnosis of pancreatic cancer. You can check for different pathways, different types of treatments. For example, have they undergone surgery, chemotherapy, radiotherapy, and you can figure out if these patients are currently alive or dead. So you can actually look at the long-term medical history. You can look 10 years back, 20 years back, and see what happens to the patients now, which means you can run 5-year, 10-year long observational studies immediately without having to wait for the data to arrive because you're actually looking at data into the past. Obviously, observational data has a huge amount of issues that need to be corrected for. The data is biased, has a lot of confounds, and it's also very related to how treatments were provided and interventions were provided at that time. But the data is all there, and we can make sense of it, and we can try to figure out what worked and what didn't work, and what is actually optimal for the patients, given all the factors that might influence it, be it clinical experience, the treatments that are available, or even the socioeconomic or ethnic settings around your own hospitals, for example. You can also start understanding how hospitals work. So for example, if you take very simple data, such as patient X has moved from place A to place B at this specific time of the day, you can create graphs like the one below, which shows you how different patients are moving around your hospitals and how many patients are in different wards. And the thickness of the lines tells you the transition probabilities between all of these different states. So you can start understanding where everyone is in your hospital. And you can then start predicting things about that. For example, you can start saying tomorrow, this is where they will be, or maybe on Saturday, this is where they will be, which means you can start asking clinicians, for example, to come in, or nurses to be available to make sure that we have enough patients to care for. You can also start finding previously unseen patterns. So this slide was actually made prior to the COVID pandemic. This slide is maybe 3 years old, but it actually is very applicable now. So this was just looking at flu-like symptoms, so terms related to flu symptoms that are written in discharge letters of patients that came through A&E or inpatients or outpatients. So any kind of a clinician saying the patient had a cough or had a symptom that is related to flu. And what you see is that there is these peaks of flu symptom counts at the hospital level. And you also see that these flu symptom counts are very highly correlated with positive samples coming from the lab for things like H1N1 or H3N2 viruses, which are flu viruses. And actually, if you do the statistics and the analysis, you can actually see that the values of flu-like symptoms start ramping up 3 to 4 days before you start having these positive samples coming out of the lab. So you can see the impact of trying to understand how pandemics work. And actually this technology, I don't have the picture here, but we've created something that we call the COVID Canary, which is exactly the same system, but everything is about COVID rather than flu. And that data is actually being fed to governments and to the different committees in government that require that data to make decisions, because it gives them a picture of what's going to happen 4 to 5 days in advance, actually further in advance than many other systems that currently exist in the UK, purely by looking at the usage of certain terms in clinical discharge letters, which is something that is incredibly simple. So step 6 is actually very related to what Ben was talking about before. This is really about automating expert and expensive tasks. So if you want to, for example, be able to label some digital pathology data, to be able to count how many cells of certain types or the shapes of those cells, if you want to, for example, contour regions of interest for you to be able to deliver your radiotherapy planning on your patients, or to be able to target a specific cancer. All of these different things are not only expert driven, so experts tend to be the ones doing it on a one-to-one basis. They're also very expensive because they tend to be very time consuming and they require a lot of resources. So many of these technologies now AI technologies can be used to automate many of these processes. And in certain situations with quality and accuracy that can bypass certain experts, actually, it probably doesn't bypass most experts, but they would at least bypass clinicians that might not necessarily have an expertise in that specific area, but might still need to care for those patients. But they can definitely automate and make sure that the service is available throughout, for example, throughout the UK. So if you have radiological service provision, which is currently, for example, one of the hardest hit specialities in terms of numbers, there's a massive backlog of and need for radiologists, and we just cannot train enough of them. If we have systems that can start reading and maybe reduce the workload of radiological care and radiological reading time, maybe we can actually cope with the current clinical availability that we have at the moment. So it's a bit about how do we make sure that we can care for patients quickly, that the expertise is available through the use of algorithms, but also so that we can make sure that these expensive tasks are used pervasively throughout the NHS. So if you've done all of this that I've described so far, these first 6 steps, you have all your data in a nice way that you can then learn from, and you can train these algorithms to be able to learn how to solve these tasks. The problem is, if you solve this problem on a per hospital basis, you're going to be incredibly biased by the surrounding population of your hospital. For example, if you go to one of our hospitals, King's College London, and another one of our hospitals, Guy's and St Thomas, they sit in 2 different parts of London. They have incredibly different socioeconomic dynamics around them. So the populations that are seen at Guy's and Thomas and the populations that are seen at KCH are incredibly different. And an algorithm that is trained at Guy's and Thomas and on Guy's and Thomas's data might not have enough reliability and resilience to variations and population variations and imaging variations that you might see elsewhere. So what we need to do is to create a mechanism so that we can train on data coming from multiple sites in the UK. And the way that we have been doing that so far, and pretty much failing at doing that, is to centralize all the data. So initiatives like HDR UK and many large clinical studies have tried to put the data in a single safe haven, single place, and centralize all this data. But obviously that comes with data privacy issues, anonymization issues, governance issues, problems with ownership and IP, bureaucracy, and all of these other complexities that comes with centralizing data. So what we decided to do with our AI center was, because we're building this common infrastructure, data infrastructure across all of these different hospitals, we decided to link them up in what is called a federated network. So that's a mechanism for you to be able to train algorithms at scale across all of these different hospitals. And by training these algorithms at scale across all of these different hospitals without having to share data, so the algorithms are the ones moving between hospitals rather than data, you can still have access to the data and scale to many hospitals and large population that is needed to train these algorithms accurately without having any of the privacy and anonymization and governance issues that normally come from centralizing information. And we are testing if this model would actually scale from our current 3 trusts to the 10 trusts of this phase 2 of the AI Center, and hopefully in the next few years to the remaining 273 trusts of the country. At least that's the ultimate objective of this. Step 8 is you've now have this mechanism to go from non-harmonized clinical data into models that have learned from that data and are actionable. They know how to action the data. They can transform the data from its raw form into a form that the algorithms understands, and they can take that data that the algorithms understand and make sense out of them and make predictions, which will allow you to then start diagnosing and prognosing and caring for patients and doing all of these things that we promised to do. So it's very important that we have the IT systems, the hardware and the software stack that is able to do this. And all of the software stack that we've been creating for our AI center is now fully open source, or is at least parts of it are, but all of it will be open source at some point. And the idea is that that becomes a national standard for the NHS to use. And the last step of them all, and this is just to finish the presentation, is now that you've collected your data, you standardize it, you train your algorithms, you now need to have a reliable system for you to deploy those algorithms and make them use on a day-to-day basis live on clinical data. And for that, we have created this AI deployment engine, which has actually been announced and released just a week ago at one of our trusts. This is the first minimum viable product delivery that we've done. So this is now in production, and is an algorithm, is a system that where you can deploy multiple apps. You can think about them as apps, but what they are workflows comprised of multiple AI algorithms that can use data live coming from clinical systems, analyze that data, and push results back into the same clinical systems from where they fetch the data in advance. At the moment, the area of application that we've demonstrated it on is in the area of stroke and improving stroke care. But the idea is that the platform is flexible enough to allow you to deploy any algorithm for any purpose that you might want. So just to finish up, the use of AI and all of these mechanisms of trying to collect data and harmonize data and learn from it and then deploy it, the ultimate idea is to try to shift to the right these curves of outcomes and costs. So we don't want necessarily to save money. The amount of money we spend is, I wouldn't say is affordable, but is doable for a country like the UK. But we definitely want to be able to continue improving the quality of outcomes for the same costs. And the way that we do this is by bringing expertise and evidence that is collected by these AI algorithms and applying them to real world data. So ultimately, what we want in the end is to really try to untap this value in retrospective data. We want to create an ecosystem for data and algorithm training and delivery in NHS trusts. And we also want to work with startups and industry to be able to make sure that these tools are actually deployed with the right level of security, with the right level of medical device certifications, and etc., so that we can have the impact that we all want the AI to have. Thank you. And I'll stop sharing now and open for Q&A.
All right, so thank you very much. That was a really excellent talk. One quick question, and then we're done. In cancer research, which is what I've spent most of my time working in, we have a sort of paradigm of very rigorous trialing, collecting data very rigorously, and then generally analyzing it using classical statistics. And in a lot of the work that you've been describing, you're talking about sort of pulling data out of much less formally recorded systems in a real world context, presumably putting them through AI kind of analyses instead. I was just wondering where you saw those two kind of different worlds.
Absolutely. That's a brilliant question, and it's something that I ask myself all the time. So there are two main usages of data in these kinds of large-scale data collection systems. Either you can do it for discovery, which is what these trials you're talking about are mostly about. You want to know something more about the data that you didn't know before. And for that, you need the data to be incredibly clean, because you want to make sure that you don't have any biases or any other weird things happening with the data, that what you see is what you see. But when you deploy this in the clinical world is messy. You will always have missing data. You will always have data that is collected in a biased way. This is the nature of clinical care provision. So if we want algorithms to work in the real world, we need them to know how to behave around the dirtiness of the data of the real world. So for real world AI algorithms that do not have a very stringent requirement list, which normally makes them not usable in a real world clinical setting, you actually need to train them on observational data with appropriate controls. So I'm not saying one is better than the other. They have different purposes, but working with observational data and making sure that the algorithms are resilient in that setting, make sure that when they are deploying to the real world and something goes wrong, the algorithms don't give you a completely wrong answer because they are expecting the data to be perfect. And I think there's a balance to be had there. But I think also the ultimate outcomes and aims are very different.
Okay, really nice answer. So let's take a break there. We're running 2 minutes behind at the moment. So we'll resume at 27 minutes past 10. If you turn off your video and mute and come back then. Okay, so it's 27 minutes past 10, so it's time to resume. We've got another 2 talks coming up. We're aiming to get through those by just about 11:15 or so, and then to have another break, and then to have some group session work. So the first talk is the second session is by Alison Kennedy from STFC Hartree. Alison's the director of the Hartree Centre there, which is a kind of a high-performance computational centre, and she's going to be talking about how we can work with the Hartree Centre on data challenges for cancer.
Hi, can people see my screen?
We can see you, Alison, but we can't see the slides.
Hold on. Right, sorry about that.
That's okay.
This worked when I practiced it before.
That's always the way.
Always the way, isn't it?
Always the way, yeah.
Right. So, sorry, I've got too many windows open, so I need the share screen button. Start again. Right. I can share your screen if that helps you, Alison. Okay, wait a minute. So is it shared at all now?
No, and this is strange because I definitely tested that this did work this morning at 9 o'clock.
Right. Right, sorry about this. Well, would you be able to play my slides for me then? Because I don't know what's gone wrong.
Yeah, do you want me to do that for you?
Yes, please.
Yeah.
Yes, please.
Or Lucy, that's fine. Yeah. Okay, Lucy, you go ahead.
Okay. Okay, that's great. So good morning, everybody. Sorry for the slight delay. So this is going to be a slightly different type of talk. I'm going to mainly be talking about the capabilities that we have at the Hartree Centre and the opportunities for collaboration. So the first part of the talk, I'll talk about what we do. The second part of the talk, I'll give you some examples of the types of projects that we worked on. And the intention there is to give you, is that the two parts of the talk will give you an idea of the capabilities and perhaps spark some ideas about how you can collaborate with us. So essentially, we're a centre of about 100 technologists. Everybody has a science degree or an IT degree, but we're not experts in, we don't set ourselves up as scientific experts. People are there as technologists. It's primarily their skills in computing, their skills in high performance computing in particular, high performance data analytics and AI that set them apart. So we're very much about collaboration, about working with using our capabilities to work with other people to bring about results. Next slide, please. So the Hartree Centre, for those of you who've not come across it, is a high performance computing, data analytics and cognitive technology centre. That's part of STFC's national laboratories. So the work that we do is based on 30 years of experience in simulation and modelling and in data analytics, primarily in the scientific domain. And the government about 5-6 years ago came up with the idea that it would be good if the sorts of skills that we've developed in STFC could be applied primarily to industry and public sector challenges so that we could translate some of that technology. So in particular, we work with businesses and applied researchers, and we're very much, as I said, about collaboration. How, if we provide access to technologies, facilities, and scientific computing expertise, how can we use that to bring about productivity improvements or improvements in health and a whole range of other areas? Next slide, please. So our particular motive, our particular mission is to transform UK industry, because that, we get our funding from the Department of Bays. By increasing the adoption of high performance computing, high performance data analytics and cognitive technology, increasingly cognitive technologies. But as I've said, it's very much through challenge-led research and innovation. So what this means is the way that we work is we have a team of business development people, we have a team of scientists, and their role really is to speak to potential collaborators and to find out what these challenges are, what sorts of challenges are out there that we can potentially solve, either by using fundamental research that's undertaken in the UK or elsewhere, or applying things which are close to market to solve particular challenges. So it's very much about demonstrating that there is an innovative solution out there and that we can apply it to a challenge. Next, please. So being a science organization, we can work across a range of areas. We could do very many things, but we focus on areas where the research councils and STFC in particular have skills which can be transferred. But as I said, it's very much about looking for solutions and techniques which can perhaps be developed in one area and translated across to other areas. So you'll see that health, well-being and life sciences is one of our 6 priority areas, and the projects that I'm going to talk to you about today come from that area. Thanks. Next slide, please. So to talk to you a little bit about what a typical project with the Hartree Centre looks like. So as I've said, it's very much about balancing the need to find something which is addressing an industrial, a scientific, an economic or a societal challenge, whilst also advancing UK capabilities in digital innovation. So it's very forward looking. It's about how can we take the latest techniques and try and address them to a current problem. So the objective is to develop new capability in core technology and applications areas, which we can then look to apply across a range of different sectors. And of course, in doing projects this way, we need very strong engagement from external organizations. So this extends from, typically it's other people's data sets that we're working with. To build on what George was saying, we need engagement with them to understand the data, to make sure that any conclusions that are recommendations that we draw from that are accurate. So we are really there to provide the technology aspects of exploring solutions, but it really has to be a partnership. Similarly with AI, we need to know exactly what the model is going to do, whether it's going to come up with the sorts of results and make the sorts of assumptions that people are happy to accept. So it's very, very much a partnership, what we're doing. Next slide, please. The way that we go about our work, we work in 4 particular different areas. So the first and the most important one is the collaborative R&D area, where it's very much about building a team of people, both at the Hartree Centre and at collaborating and partner organizations to deliver a solution to the challenge that we've identified together. So typically what we're looking to do is to develop so-called T-shaped teams, where you have a range of expertise in different areas, but you also have depth in that, so you can really get into and understand the challenge. So these are the types of things which can't be done by one organization alone, which is why it's very important to have these partnerships. We have some very good technology available at the Hartree Centre. So one of the other services that we can offer is platform as a service. So that's typically for organizations which have done their own development or they've done their own research, but they're looking for access to visualization facilities, high performance computing, AI systems or whatever, so they can run their own research on a bigger system than they'd have access to otherwise. So much of the work that we do on projects is producing deliverables, software deliverables. So this can either be tools or it can be building blocks that are part of something bigger. So these so-called digital assets, we can either create as open source and make them available to the community, or we can license them to particular organizations and applications. So that's another aspect of what we do. And very importantly, training and skills are essential to encourage adoption and to increase understanding of both the limits and the benefits that data analytics, AI, other technologies can bring about. So that's another important part of what we do. Next slide, please. We've been very fortunate this year that we've attracted a large amount of government investment into a new venture called the Hartree National Centre for Digital Innovation. So it's part of a plan to position the UK as a global leader in the applications of AI and HPC, primarily by industry, but also the public sector. So we have £172 million worth of government investment, which will go into people, computers, facilities, and will be invested in the northwest of England. We have a partnership with IBM, who are co-investing £38 million into the centre. And we have a team of IBM staff who work with us on site. So the thinking there really is that although the UK is investing heavily in AI, companies like IBM also have a massive budget, and AI is one of the areas that's very important to them. So it gives us access to IBM IP, which we can use on projects to supplement the work that's done in the UK. So essentially, we'll do a range of different things, which I'll talk about very briefly. And we're looking to produce economic impacts, so increases in productivity, upskilling the workforce, and making computing technologies more widely available. So the 4 aspects of this, which really mirror what we do in all our projects. The first part, explain, is about increasing training at all levels, so that we have a bedrock on which to build, and that technology transfer to companies and to organizations is much more successful. There's also a program in which we work with SMEs in particular, to provide them with additional support. The Explore program will do a huge range of proof of concept and proof of technology projects in AI. And then for a few of these, we'll work much more closely with companies to accelerate the technologies and get them taken up across the industry. And the final work stream here is emerging technology. And in particular, we'll be looking at quantum computing. And are there research challenges out there which can be solved, potentially solved in years to come by quantum computing. Next slide, please. So now I'm going to go on to talk a little bit about our track record and the sorts of projects that we've done. So at this stage, I was also going to mention, I've focused primarily on healthcare projects, but there are also projects in other areas where the sorts of tools and techniques that we're using can be applied to projects in the life sciences, cancer research, and other areas. So for example, George was talking about natural language processing. To date, we've done some projects in areas which are probably easier, and less ethical concerns than healthcare. We've done projects in legal services, whatever. So that's an example of an area where we've done some work which could be translated, but hasn't been yet. So if you have ideas for projects in areas that I'm not talking about, then we're happy to talk to you about whether or not we could support them. Next, please. So the first project that I'm going to mention is one that was in particular about improving the accuracy of breast cancer diagnosis with machine learning. So mammograms are not suitable for all women. Ultrasound is apparently much harder to interpret. So we worked with a company who came to us called Oncolite, who were wanting to develop tools that would help radiologists screen breast ultrasound images for cancers. So we used computer vision neural networks to build a model which would classify images as healthy, benign, or malignant. And the intention here was to develop a tool which would improve the accuracy of the existing tools and boost the diagnostic accuracy. So that's one example. Next slide, please. The next one also I think harks back to something that George was talking about, and it's about predicting the demand for particular services. Really about resource planning and knowing when interventions were needed. So we worked with the Liverpool Clinical Commissioning Group in particular to build an AI model for alcohol-related hospital admissions. So pre-pandemic, 74% of all hospital admissions were related to alcohol consumption. So the challenge here was to see if we could look at data from a range of different sources to identify which patients were at most risk of emergency alcohol-related interventions and would need to be brought back into hospital. So the idea there was to target interventions, identify what the risk factors were, and to plan better services. So again, we used machine learning tools that would build models to select the most relevant features from diagnoses, patient histories, demographic data, and deploy a live working tool across Liverpool that would flag high-risk patients. Next, please. The next project is one we did 3 or 4 years ago with the Alderhay Children's Hospital. And the intention there was, could we use AI to develop apps and tools that would enable the medical staff to spend more time with patients when they were in hospital by reducing the number of no-shows and by answering some of the questions which patients would have before they came into hospital. So this was very much about understanding what sorts of things people were worried about before they came into hospital. Could AI be used to diagnose anxiety, particular anxiety from people about coming in for their procedures, so that they could be provided with more information before they came in? Could we use AI to follow up on patients by seeing some of the questions that they'd done when they went home? So this is part of the Alderhay Children's Hospital Cognitive Program. Next, please. We worked with a company called Orca, who are very much into digital healthcare, to see what we could do there to help them evaluate a particular data-driven approach to healthcare. So what sorts of apps would they be developing? What was the demand for that? How should they be developing and growing their business to incorporate yet more data science techniques? What should they be bringing in? What sorts of new roles should they be creating? How would that help to future-proof their products and their business? So that's an ongoing collaboration which has been very successful. Next, please. And then this again is an older project which we did about 3 or 4 years ago. So we have very good visualization facilities. We used visualization to build a very large model which people could come in and interrogate using PubMed, which has a huge number of citations, maps all known human diseases, and has huge amounts of information. So by doing that, researchers came in and were able to identify some areas that would be beneficial to them, that people like us who do the data science can't see what the real benefits are, but once you bring in clinicians and drugs researchers, they can see what the benefits could be immediately. Next, please. And I think that the final one that I'm going to talk about is drugs design. So that there's huge challenges in developing new drugs. How can it be done more quickly? How can it be done to increase productivity? And what are the particular challenges that we can use using simulation and modeling, AI, data analytics to try and predict structural behavior in novel chemicals? Because of course the aim is to produce drugs which are easy and quick to produce and that are relatively cheap. So we worked very much with scientists to look at how we could use molecular simulation of encapsulation to pre-screen as much as we could on hard to manufacture chemicals before the lab-based work. The other side of that work was we discovered in working with scientists that they were very much interested in how we could make the whole process more user-friendly. So another part of that project was looking at computational notebooks that would make it easier for the scientists in the field to work with us and to understand and record what was going on. Next, please. So that's all that I was going to say today. So hopefully that's given you some overview of the types of things we can do at Hartree. And the take-home message really is that we're very keen to collaborate with a range of people. Our mission really is to use technology to help to solve some of these challenges. And there's obviously huge challenges in this area. So thanks very much.
Okay, so thanks a lot, Alison. No questions showing up on the chat yet. I've got a question. With the ultrasound study that you did, you're saying that ultrasound is more difficult to interpret than mammograms. So presumably, though, it must have advantages because otherwise it wouldn't be done. And so is it the case that it's just that the interpretation is more variable, so it's more user dependent, and that is why an AI approach could help because it would kind of standardize it to the levels of experts?
My understanding, and my understanding is not a deep one, is that mammograms are much easier to understand, but it's also the types of patients who are not suitable for mammograms perhaps have a different density of breast tissue, which makes it more difficult to interpret it. So it takes much longer, it takes more expertise, it's probably less common as well. So it is an area where applying AI can bring benefits.
Okay, and the point there that it doesn't give a radiation dose as well. Okay, and then one very practical question from Laura, which is, what is the best way for our community to actually get started with working with the Hartree Centre? I mean, do you run kind of courses or events or anything? We
do run courses and events. We have, as I said, a large number of business development managers. We have a help desk. So anybody who's interested, we have channels that you can follow as well. We've got Twitter, we've got websites, we've got LinkedIn. But anybody who wants any more information or is interested can email me in the first instance, and I'll pass you on to the right business development person, and we can take it from there.
Okay, and then one more question along the same kind of practicality, which is typically, how long is the application process to get a project up and running?
It depends on the funding source, I think. So basically, what the business development managers and the project scientists will do is they'll go out and they'll talk to you, and we'll identify, is it something that we need to apply for specific external funding for? Is it something, is the data in place, so it's really about scoping out the project and checking that we have the right person available. So some of the bigger research projects obviously have to go through, peer review, and we have to bid for external funding. So that takes a bit longer, but typically we can start up smaller projects fairly quickly.
All right, very helpful. So thanks very much for that. That was really good talk. So we're absolutely right on time at the moment. So the final speaker for the morning is James Nightingale, who's a postdoc at Durham. He's an observational cosmologist. I was down at the Marsden for kind of a career celebration day about 2 years ago, where someone was saying that the amount of data available for cancer research now is approaching or exceeding the levels available in cosmology. So that seems to be the sort of starting point for what James is going to describe. And he's talking about links between the statistical approaches that are taken in cosmology and those that might be used for cancer treatments.
All right, so can I just check, is my voice clear? Is my screen sharing everything?
Yeah, that's all fine.
Brilliant. Okay, yeah, so hi everyone. I'm a cosmologist at Durham University, James Nightingale, and as just said, I'm going to be talking about a project where basically I'm aiming to take statistical methods and techniques I developed to do cosmology research and apply them in a healthcare setting on the problem of cancer. So I'm going to talk about this notion of multi-scale complexity, which is kind of the phenomena that brings together these two seemingly quite disparate, different fields of research, cosmology and cancer. I will quickly go through the cosmology just to add context, but we're obviously going to dive in and focus on the healthcare side of things and the multidisciplinary aspects. So yeah, let's begin by multi-scale complexity to try and give you sort of context of where this all came from. So a multi-scale system is a system where the components that make up that system vary by orders of magnitude by some measurable property, their mass, their size, or whatever. And the largest multi-scale system you can probably envision is that of the universe. We live on a planet, the Earth. We orbit a star many thousands of times our mass and size. If you take millions or billions of stars, you'll form galaxies like the Milky Way. Galaxies actually come together to form larger observable structures in the universe, the largest of which are galaxy clusters that contain thousands of galaxies. And these components make up our observable universe. And so this is what multi-scale systems are. Multi-scale complexity emerges when, despite the huge orders of magnitude difference in scale of these things, they somehow show causal interdependence. They're causally related. So the way that the stars, like the sun, emit energy changes the way that galaxies appear. This changes the structure of galaxies, which changes how they come together to form these larger structures. This changes the makeup of our universe. But this multi-scale complexity goes in two directions. The laws of physics and gravity that govern the universe ultimately dictate these structures, dictate how galaxies appear, and so on. So this is the sort of way that I approach studying cosmology. And just so you're all on the same wavelength where I'm going with this, why am I talking at a healthcare conference? I will obviously go on to discuss that it's viewing biological systems with this sort of same multi-scale hat that I think there can be progress, or it's a different insight that one can take. But before we get into the healthcare side, the biology side, I'm going to quickly just go a little bit more into cosmology so you can get a sense of how I made this transition to healthcare. So my cosmology research focuses on studying dark matter. You've probably heard about it in mainstream media. We as cosmologists have learned that the majority of matter in the universe is not baryonic. It's not the stuff made of electrons, protons, hydrogen, helium, the stuff we can see and touch around us. But it's actually this dark matter that's completely invisible, and it only interacts gravitationally. We've observed it through its interactions in gravity. So it's an interesting phenomenon. It's a huge problem in physics. The reason I'm talking about this is to try and portray how we've come to get this picture of our cosmological model. So the observation that kind of established dark matter as the cosmological model today was the cosmic microwave background. The only thing you need to look at here is this map of blue and red dots. Each of these blue and red dots are light rays that have traveled the entire observable universe, that's 14 billion light years, and then been observed by us. And by observing these, we've been able to kind of piece together what the universe looked like at its formation. And we've been able to use that to kind of work out that there must be this dark matter. So what I'm trying to get at here is, from a multi-scale system perspective, we observe things over the entire scale of the system to constrain our models of the system itself. But we do this over every scale. We also, for example, myself, look at individual galaxies. And it's the dark matter, by looking at the rotations of stars in those individual galaxies, we worked out as early as the 1930s, the need for this dark matter. The stars were rotating too fast for there not to be this kind of missing component that must be acting gravitationally. What I'm trying to get at here is, we as cosmologists have been conditioned to kind of always think about our scientific analysis and study with this multi-scale perspective. We can't just look at one component of a system and try to use that to constrain our sort of overall picture of the universe or the models we're interested in. And that's where the sort of insights that I've got that I kind of are trying to take into healthcare. But more practically, it's not just about having insight, it's about actually having tools and methods and statistics that allow for that transition. So at the core of my cosmological research, what I'm really doing, or unbeknownst to me had been doing, was developing open source statistics software, Bayesian methods that facilitate and allow for the detailed analysis of multi-scale systems. And these are what we're going to apply in healthcare. So I'm not going to go into the details of all the Bayesian stuff. I've listed some buzzwords here. The main point is the way that this software works is you can take data sets across many different scales, galaxies, the cosmology of the universe, data sets that represent stars, and it's about building a sort of a hierarchical overall Bayesian model that uses all of those data sets to try and piece together a wider picture, rather than just looking at one specific thing and trying to sort of generalize those outputs. And so the thing I'll emphasize when I talk about multidisciplinary research is, in order to do this, everything was done open source. We set out from day one to develop a fully general software implementation with the idea that this would ultimately see application outside of cosmology. And for multidisciplinary research, I cannot state enough, it's imperative that you do things open source, but it's even more imperative that the quality of software you develop is, at the top level. If it's not, it just doesn't work, which is something I've learned the hard way over the past 5 years of my research career. Okay, so that's the cosmology. As I say, it's probably not the most relevant thing for this conference, but I'm trying to give you some context of where I got to when I started this sort of transition to healthcare. I'm now going to try and talk about the cancer, but I want to get a few caveats out of the way. Of all the people at this conference, I'm probably the least qualified to talk about cancer research. My PhD was in astronomy. I'm a cosmologist. I do statistics software. I'm only just kind of now wrapping my head around the literature for this. So, a lot of what I say might be an oversimplification. A lot of what I say might seem a bit, inaccurate. But the point is, I'm trying to give you the sense of how someone from the outside looking in is sort of viewing this literature. And hopefully that's a worthwhile thing for me to discuss. But don't yell at me if you think you're outraged at anything I say. Okay, so let's now focus on biology as a multi-scale system. And again, I'm sure you're all aware this notion of multi-scale complexity is right here. You could come down to the the genomic scale, the DNA, which I'm going to talk more about in a moment. And clearly, our genetic code is what defines ultimately what proteins and other such things we as humans make. And it's the complex interactions between proteins that ultimately form things like cells, and those cells signal through signal pathways communicate with one another. It's very analogous, at least to me, as how I view the universe. But conversely, again, we could argue that the multi-scale goes in both directions. The way that we interact as a population ultimately dictates what happens at these smaller scales. If we all smoke, our organs get less healthy. If we all live in nuclear reactors, our genetic code gets mutated and changes. That's an extreme example, but you get the idea. So what I want to do is just try to basically explain how I, as a cosmologist, would try to use this to sort of better change the way we approach modeling in biology. And I'm being wary here because I think I'm trying not to overstate what I'm saying as the outsider. So the genetic code of an organism is now something we have incredible access to. Advances in computation allow us to basically do whole genome sequencing of most organisms, including, of course, humans. You all know this better than me. The Human Genome Project, nearly 2 decades ago, basically mapped out the entire human genome. When I'm talking to the general public about this, I describe it as the Lego of a human. And the healthcare implications of this are seemingly very obvious. If we can map out the genetic code of a healthy individual, and we can then compare that to a patient, surely we can use that information to diagnose diseases like cancer or whatever. At least that was the idea. And indeed, industry jumped on this. They've worked tirelessly over the past couple of decades in order to make whole genome sequencing extremely affordable. There was this $1,000 genome project, which clearly was successful in roughly the mid-2000s. And as I was saying, at least the outlook in the early 2000s was that surely this was going to completely revolutionize healthcare. For prevention, as I described, you could look for genetic mutations in an individual, correlate them with certain cancers or whatever, and perform intervention. And if someone does have symptoms, you can use this to get an evidence-based diagnosis for that individual. And there's also pathways to use treatment. Now, I don't want to understate how important the Human Genome Project has been. I have no doubt it's made huge revolutions in many different aspects of scientific research. But the picture that some, I guess, perhaps optimists were looking at in the early 2000s of how this would revolutionize healthcare never really came to be. I personally have not yet had my genome sequenced to have, by the doctors. No one I know has, and this doesn't really seem to be in and of itself, in a closed box, the only thing, the way to approach this. And the reason for this, as I'm sure you all were more aware than I was when I started this project, is that, to put it simply, causation is simply more complex than that. The notion that single genetic mutations, the notion that just looking at the genome of an individual can be used to diagnose something as complex as cancer and many other diseases, this has effectively been falsified. And I guess as a cosmologist, my viewpoint is, as I'm hopefully many of you share, is that this tool of genomic sequencing, the human genome in and of itself, is a building block of a multi-scale system that we must basically study and model and analyze over all of the different scales and connecting them together. So, for example, we can take the whole genome sequencing of an individual, but we have to supplement that with other data on that individual in order to understand how their specific genetic code may lead to the formations of proteins and so on, which themselves then have complex interactions. And it's understanding those complex interactions that we may be able to work out which mutations are most likely in that individual that can lead to the formation of malignant cancer cells and so on. So, I don't know if I'm saying anything particularly new here, but as a cosmologist looking in, this to me is sort of something that doesn't always seem to be, portrayed fully in the literature. But nevertheless, don't get me wrong, there is a huge body of literature that is going in this direction of studying biology as a multi-scale system. So I'm not saying anything new here. I think what I'm really trying to state is that the way that biologists can think about this problem is not in and of itself unique. There are lots of scientific disciplines, whether it's cosmology or others, that are faced with these problems. And it's, I think, by working together that I think there's huge amounts of insight that you can gain from one another. But also more practically, we all use different statistical tools and techniques and methods to study these types of systems. And by communicating with one another, I think there's a huge amount that we can learn. I've certainly learned so much working with healthcare researchers, and hopefully they've learned a bit from me. Okay, so that's kind of me trying to just give in terms of the research, a portrayal of how these sort of different research fields come together. I'm going to try and, back this up with a bit more actually, like what are we actually doing? So who am I working with? How are my methods actually kind of making their way into practical research? So the partners that I collaborate most closely with is a UK startup who focus on developing models of cancer therapy for treatment and diagnosis. They're called Concur, they're based in Cambridge. And basically they sort of share my view that the one way to approach healthcare diagnosis and modeling is this multi-scale approach. The term they use, which I guess is quite apt, is multi-omics, where basically it's combining data sets of all the different omics in this hierarchical fashion. Genomic data with proteomic data with whatever else you have going up in the scales of complexity. And so ourselves, Concur, the NHS Christie Trust Foundation, and the pharmaceutical company Roche, who are leading this, are working together on an Innovate UK grant focused on the diagnosis of carcinoma of unknown primary site, or CUP for short. So this is basically where malignant cancer cells are found in an individual, but their origin is unknown. They don't know if it was lung cancer, breast cancer, pancreatic cancer, whatever. And whilst it's not the most common cancer in the UK, despite this, it is one of the leading causes of cancer death. And the reasons for this are hopefully very obvious. If you don't know what the origin cancer was, you don't have a clear pathway for treatment. You don't know which therapy or immunotherapy to put the patient on. And indeed, in the UK, there's no approved diagnosis tests for doing this, for example, using genomic data. So this Innovate UK grant is basically about us trying to address this problem, or seeing if this type of modeling can help. So this is what we're doing. We're trying to basically apply this kind of multi-scale modeling technique to data that we've collected in clinical trials on CUP patients, and use this to create evidence-based probabilistic assessments of their most likely origin cancer, and hopefully then have a pathway to treatment. And for me, I guess as a statistician, I think CUP is a brilliant starting point for this type of problem for two reasons. The first is that you know the individual has a cancer diagnosis. So you've got a very strong prior that you're looking for something, which simplifies the problem a lot compared to early detection and diagnosis. And the second reason is because this is a clinical trial, you can collect all the data sets, not all, but you can collect a large amount of data on these individuals so that you've got the data you need to see if this type of modeling can work. And once you've got that kind of demonstration, that proof of concept, then you can begin to ask, would this type of approach, would this type of philosophy work with these much harder problems like early diagnosis? So I'll say we haven't got final results yet. We've had major delays due to COVID. I think our clinical trials started a few months ago, but hopefully in the next year, you'll see, output from this, whether this was successful or not. And so I'm about to go on to the multidisciplinary stuff, but yeah, basically we are working together on building kind of a unified statistics framework that will allow I, as a cosmologist, to analyze images of galaxies and whatever else to work out global properties in a model, or simultaneously collaborators in healthcare can use the same statistical framework to analyze genetic data, proteomic data, and whatever else to basically try to track global trends in cancer, make informed decisions on the best ways to diagnose and treat cancers. Okay, so I've got 4 minutes left, and I wanted to kind of just describe my experiences working in a multidisciplinary team as someone who is a bit of an outsider, and I think it's hopefully informative, and it makes sense, right? If multi-scale systems are thinking about the problem in this way is the approach one is going to follow, it necessitates having teams from a huge variety of different backgrounds, scientific fields, with all of the different domain expertise necessary, of which I fit in a small nugget of this. I think it goes without saying, this is how it has to be. And so what are my experiences? When does multidisciplinary research go right? And obviously, conversely, when does it not? And so the biggest take-home point, if you take home anything from this talk, I would say is on the importance of effective communication in multidisciplinary teams. Okay, so what are we looking at here? This is a gravitational lens. These are the astronomical systems that I, as a cosmologist, study. We've got us on the Earth. We are pointing a telescope at a distant galaxy in red here. And between us and that galaxy is another galaxy. And the gravitational field of that intervening galaxy is curving space-time such that the light rays from this background galaxy bend around it, meaning we observe this galaxy multiple times. And you, who have never heard of a gravitational lens before this, could now perhaps start to think how you would build a statistical model of this system. You might think, well, I've got two galaxies. I'm going to build a model that separates these galaxies into a background galaxy and a foreground galaxy. And then I need a model for the galaxy's light, I need a model for the galaxy's mass, and I need a model for the background galaxy's light. Why am I telling you this? Why am I rattling on about gravitational lensing in a talk for STFC cancer diagnosis. It's because through astronomy, through this sort of very simple, intuitive way of describing a model, myself and collaborators in industry built a common language to express the statistical model both parties needed. I never needed to understand anything about genetics or proteomics or all those things, because I could express to them my statistics through astronomy. And conversely, astronomy was ingrained enough in mainstream media that they could express it back to me through astronomy. It's a really perverse thing, but working on this project, I kind of realized that this was kind of the most important thing to us forming an effective multidisciplinary team. And I cannot state enough, like if you can find people that you can communicate with somehow, it is the basis for all of this. So conversely, I think most multidisciplinary research probably dies very early on because there isn't this effective channel for communication. Other experiences I've had, I think when multidisciplinary research works, I think it works for everyone, which is very unique in academic research. Both parties have access to funding, they otherwise never would. Both parties have the knowledge expertise of each other. I've learned so much working with people in healthcare. I wouldn't expect it. I was very much the arrogant academic who thought I was going to be helping them. It was completely the other way around. And if you're fortunate, you also get interest from the press, which helps both parties raise their profiles and so on. And there's a lot of benefits compared to collaborating with academics. You're not competing with one another. If you've got your IP right, there's not really any conflicts of interest. But on this topic of funding, I've got 20 seconds left, so I'm just going to sort of round up here. For better or for worse, UK science funding under this Conservative government is all about science exploitation. As an astronomer, for me personally, this is the only way I can attract large bodies of funding, but there's huge amounts of it out there for this type of multidisciplinary research. The thing that you need is someone like myself, a scientist who is able and willing to write proposals that have literally nothing to do with their field of research. I've written so many proposals that do not mention the word cosmology. And that takes, I think, a special sort of person to have enthusiasm to keep doing that. Okay, so I will finish there and take questions. The main thing I'm trying to portray is hopefully my insights are interesting. If not, at least thank you for listening to us.
All right, so that was a really interesting talk. So any questions, welcome on chat. We've got about 2 or 3 minutes. I've got 2. The first is you'll find actually there are quite a number of physicists and engineers on the call who work in cancer research. And what happens is we all start off doing physics and we all end up doing cancer research, and we do a particular form of it. So it's always exciting to hear from somebody who is sort of in some ways at the start of that journey, and particularly to ask what insights are available. In other words, how do we stop you just turning into yet another physicist who has done cancer research and ends up going down a particular pathway? How do you take the particular skill set that you have and sort of remain true to that while applying it to cancer research?
Yeah, so I do kind of feel myself as I read the literature for cancer and whatnot, ever tiptoeing more in that direction. I think I don't know if I'd make it the whole way, but I kind of feel like what you're saying is perhaps I am on the beginning of that path. It's a very good question, of which I probably am not qualified to give the answer. I'm so early in that experience. I guess for me, it's probably heavily a funding-driven thing. I think for me personally, I could end up in a situation where in terms of funding, I don't have the opportunities open to me to stay in cosmology research, but I'd probably, if I want to stay on the academic path, I would have the funding opportunities to me to kind of go into this more practical setting. And so I think if you wanted to keep people in the blue skies research, I think you need to kind of have funding that allows them to do that whilst keeping this industry sort of link going. And I personally am finding it very hard to find funding opportunities that kind of facilitate that. They're either 100% blue skies, which is not what I'm doing, or 100% science exploitation in industry. There isn't really a way, there doesn't seem to be funding channels that put you in the middle.
Right, okay, that's interesting. And then a second question, just looking at the difference between cosmology and cancer research. So it's a while since I did any cosmology. Would it be fair to say that the mathematical rigor of cosmology is higher than cancer research, but conversely the complexity of the data structures is actually less? Because if I wanted to be provocative, I'd say that, you know, with cosmology, you've just got like velocity and mass and gravity and a bit of electromagnetism, which is pushing a bit. Whereas with cancer research, you've got, you know, like you're saying, genomics, proteomics, metabolomics, all that kind of stuff.
Yeah, so I think that's 100% exactly correct. So in my experience so far is in cosmology, let me express this correctly. It's very possible that you can do inference on a given scale and do that almost separately from other scales and connect those different scales. There isn't this sort of that level of causal, that interdependence. So the modeling is much more straightforward. Whereas I think in cancer research or biological systems, if you tried to do this on one scale and then kind of jump to the next scale and go back and forth, I think the complexity is too high. It doesn't work. That is 100% true. And the framework, the first thing we did with Concur is previously the framework for cosmology here did exactly that. We would fit a given scale, galaxy scale, and we'd flow that up and down to try and piece together the overall cosmology. As soon as we started working with cancer researchers, we started building the software and the framework that would fit all of these different scales simultaneously, because that's the only way you can model cancer or whatever and get good inference. So I think that's exactly correct. Yeah.
All right, very helpful indeed. Thank you very much. Yep. Okay.
Yeah.
So we're right on time, I think. So I will hand over